So let's go ahead and work example 2. Find a power series solution to x minus 2 times y prime plus y equals 0. Then identify the corresponding elementary function. Now notice, if I have a choice, I can solve this one once again by separation of variables. But in order to understand how the power series solution method works on more complicated equations, that's what we're going to go for here. So we'll start with an assumption about the nature of our solution. Let y equal the power series, sum from n equals 0 to infinity of c sub n times x to the nth power. Now, in our differential equation, we also have a y prime term. So as we did on example 1, we'll go ahead and differentiate this polynomial of infinite degree term by term. We learned that the derivative has one less term than the original, so we'll start counting at n equals 1. And the derivative of each term is going to take the pattern n times c sub n x to the n minus 1. So we're going to take this information and we're going to sub it into the differential equation, which, notice, has variable coefficients. First order differential equation with variable coefficients. We learned how to solve that in chapter 1 using separation of variables. So we're going to start with replacing y prime with its power series expression, n equals 1 to infinity of n c sub n x to the n minus 1. We're going to add this to y, which is represented as the sum from n equals 0 to infinity of c sub n times x to the n. And this is equal to 0 on the right side of the differential equation. Now remember, our goal at this point is to determine the undetermined coefficients. We have an infinite number of coefficients here written in efficient and condensed form. We have C0, C1, C2, C3, up to an infinite number of terms. So our goal is to find those coefficients. Now, let's do a little bit of algebra. We're going to distribute this x minus 2, or we're going to distribute our series into this binomial, and that's going to require us to manipulate the exponent on our x term. And I'm also going to separate this into two individual series. So we have the sum from n equals 1 to infinity of n times c sub n. Now, if I take x and multiply it by x to the n minus 1, I can combine those by adding exponents. That gives us x to the nth power, okay? Then I'm going to go ahead and separate this into two series. Now we're distributing the series to the coefficient negative 2, and we have the sum from n equals 1 to infinity of n times c sub n x to the n minus 1. No change on this series here. I'm going to copy it down as is, and still equal to 0. Now, my goal at this point is twofold. I want to make sure that the powers on x match. Match x to the nth. I'll be able to combine like terms if every series has x to the nth power as opposed to this one, x to the n minus first power. So I'm going to manipulate that middle series. The first one is good to go, so I'm just going to copy that one down. Now here, I'm going to add 1 to the index in order to make it x to the nth power. But recall, I have to make that a uniform change throughout my differential equation, and I have to undo that in a different location, right? I can't change it just because I feel like it. So what I'm going to do is add 1 to the index everywhere I see it there in my nth term formula. That's going to give me the x to the nth power that I need. However, because I added 1 there, I'm going to cancel that change by subtracting 1 from my lower limit of summation. So now, my lower limit of summation is 0. The upper limit of summation was infinity, and infinity minus 1 is still infinity. And no change to this last series. Okay, now all of those terms have x to the nth power in common. However, we have another problem. Our other problem is we want our lower limit of summation to match as well. So we're going to match lower limits. We need them all to start in the same place so that we can combine these three different series into a single series. Now, it's going to be difficult if for example, if I subtract 1 from this lower limit of summation, that would require me to add 1 to all of the n's in the formula, including this one. Now, if I add 1 to that n, then I have taken a step backwards because remember, we want all of the powers of x to match. So instead of manipulating it in that way, I'm just going to take out a couple of terms on those second two series. So no change here. What I'm going to do here is take out the 0th term. Okay, so I'm going to go ahead and plug in 0 for n in my formula here. When we plug 0 in for n, we have 0 plus 1, which is 1. When we plug 0 in for n, we get 2c sub 1, and then x to the 0th power gives me 1. Okay, so I've taken off my 0th term, and I want to be really clear, so I'm going to go ahead and write that down just so you know what I'm doing. And then I'm going to continue the rest of the series from 1 to infinity, and no change to the formula here. Okay, so here's my 0th term. Here's my first through infinite terms. Okay, so I just took the first term out. Now my lower limit of summation matches and the power on x matches. This is going to allow me to combine those series into a single common series. Let's do the same thing with this second one. Let's take off our 0th term. We're going to get c sub 0 x to the 0th power, and then we can represent the rest of the series from 1 to infinity. And all that's equal to 0. So now we have a couple of stragglers or individual terms here. We can combine those and bring those to the left. We'll get c naught times 1 minus 2c sub 1 times 1, and those are taken care of. Then we can combine the rest of our series, which is counted from 1 to infinity, and combine all of those nth term formulas. Don't forget the minus 2 on that second one there. So now I have a single series. Each term in that formula contains an x to the nth power, so I'm going to factor it out as a greatest common factor. So we have the sum from n equals 1 to infinity of n c sub n minus 2 times n plus 1 c sub n plus 1 plus c sub n. All of this times x to the nth power equals 0. Looks like we have a couple of like terms here. Those both contain a c sub n, so let's group those together as well. We have the sum from n equals 0 to infinity of n plus 1 times c sub n, just combining these terms, factoring out the c sub n, minus 2 times n plus 1 c sub n plus 1 equal to 0. Don't forget, our goal here is to figure out those unknown coefficients. So I can think of this right side as the sum from, whoops, I see a mistake. That's supposed to be a 1 right there. The sum from 1 to infinity of an infinite number of zeros, okay? So now we can set corresponding coefficients equal to 0. Also see a missing x to the nth power there. Okay, I think we're good to go. So if I think of this right side as the sum of an infinite number of zeros, then the coefficients on the left should all be 0, including these little stragglers out here. So we can say c naught minus 2c sub 1 equals 0. And it'll be convenient if we solve for the later coefficient in the series in terms of the previous coefficient. So solving here for c1 in terms of c0, subtract c sub 0 from both sides and divide both sides by -1/2. So we have our first coefficient c sub 1 in terms of some constant c naught. Now, second, we can recognize that all of these coefficients should also be 0. So we have n plus 1 times c sub n minus 2 times n plus 1 times c sub n plus 1, all also simultaneously 0. So we're going to solve for c sub n plus 1 in terms of the previous constant c sub n. Okay, so doing a little bit of algebra here, isolating c sub n plus 1, we're going to end up with n plus 1 times c sub n over 2. Oops, backtrack a little bit. Looks like the n plus 1s are going to cancel as well. It's going to work out really nicely. C sub n over 2. So each succeeding constant is half of the previous constant, okay? And keep in mind, this is going to be true for all n greater than or equal to 1, since we started our lower limit of summation at 1. Now, this is our recursive or our recurrence relation. We need the nth term formula for our summation notation. So let's see if we can generate a pattern and use inductive reasoning to determine the nth term formula. Now, from our first set of constants, we know that c sub 1 is equal to 1/2 c naught. This would match up with the formula that we derived here if we're looking at n equals 0. Right? Now, let's increment our index by 1. Let's go n equals 1, and then we can use this formula to determine c sub 2 is c1 over 2, or 1/2 of c sub 1, right? C sub 1, we know, is 1/2 c naught. So now we have c sub 2 also in terms of c naught. Let's go another step, n equals 2. You only need to do as many steps until you feel very confident that you can see the pattern. C sub 3 would be the previous constant, c sub 2 over 2. So I'm going to factor out that over 2 there as a 1/2. And then c sub 2 we found was 1/2 times 1/2 c naught. Again, I'm not simplifying because my goal is to spot the pattern. Now, if we continue this pattern, it's pretty obvious what our nth term formula should be. Don't forget, the nth term formula is going to express the coefficient in terms of n only, and possibly one initial constant. So notice when subscript here is 1, I have 1/2 to the first power. For subscript 2, I have 1/2 to the second power. So this subscript is going to match the power on that 1/2. Therefore, we can see that c sub n is equal to 1/2 to the nth power times some initial constant. So that's very important. We have found the definition for those coefficients, the infinite number of coefficients, in our assumed solution. We can say, therefore, the solution to the differential equation y is equal to the sum from n equals 0 to infinity. Okay, remember we started with 0 here, and we learned that the formula that we discovered here is also consistent for n equals 0. So I can lump those all into a single series. So the c sub n term we discovered is 1/2 to the nth power times c naught, and then now we have our x to the nth power. Or, if we factor out the constant c naught, we have n equals 0 to infinity of both 1/2 and x are raised to the nth power, so we can write it as x over 2 to the nth power. So this is our power series solution for the differential equation. C naught is a constant that can be solved for or determined using initial conditions. You might recognize that this is very similar to a geometric series. It just happens to be a geometric power series. And if you recall from your previous calculus studies, this is going to converge for the absolute value of x over 2 less than 1, or -2 less than x less than 2. So our radius of convergence here is 2. That means that the power series solution will converge to an elementary function for x values between -2 and 2. We've got one more step. We have the power series solution, but we want to identify the corresponding elementary function. So I'm going to go back to my list of elementary function power series expansions and see if I can match this solution up to one of those patterns. Our power series solution had x over 2 to the nth power. So if I change all of these x's to x over 2's, I would see the power series expansion that we just determined. If I replace this x with x over 2, we need to replace this x with x over 2. So our elementary function then would be 1 over 1 minus x over 2. Again, I'm just replacing this with the new argument. So back to our solution here, y is equal to c naught times 1 over 1 minus x over 2. Okay, if we simplify that algebraically, we would get y equals c naught. I'm just going to multiply the top and the bottom by 2. So we'd have 2c naught divided by 2 minus x. Okay, and I am going to preserve that 2 next to the c naught so that I can see how this constant relates to the one from the power series. So we solved this using a power series method. It was pretty involved, long and drawn out. If you go back to the original function and solve it using separation of variables, you're going to get the same solution, but it's only going to take a few seconds, 30 seconds at most, if you're a good integrator. So again, the purpose of working such a simple problem with such a complex method is because this complex method will solve more complicated differential equations that our simpler methods cannot handle. Let's spice it up just a little bit here on example 3 and solve a second order linear differential equation. Notice we do have constant coefficients here. So we could either solve this with making a substitution to reduce the order of the equation, or we could solve it with a characteristic equation. But instead, let's explore the power series solution method to solve y double prime equals 4y. We'll get a power series solution and then we'll convert it back into an elementary function. As we did previously, we're going to start with an assumption that our solution can be represented by a power series. Let y equal the sum from n equals 0 to infinity of c sub n times x to the nth power. Remember, an infinite degree polynomial converges to some elementary function. Now, for this particular differential equation, we're not only going to need y prime, but also y double prime. We've learned that y prime starts counting at n equals 1, and we obtain n c sub n x to the n minus first, just applying the power rule there. So we're going to do another iteration of that derivative here, the second derivative. Now you can see this one's going to start at n equals 2 to infinity. We're going to bring down that next power, n minus 1 times c sub n times x to the n minus 2, decreasing that exponent by 1. Now, as we've done before, we're going to sub this into our very simple differential equation, y double prime equals 4y. So replacing the left side with our power series derivative, we have the sum from n equals 2 to infinity of n times n minus 1, c sub n times x to the n minus 2. And on the right side, we have 4 times the sum. Now back to our assumption for y, n equals 0 to infinity of c sub n times x to the nth power. Note we have two problems. The powers on the x's are different. We want those to be the same so that we can combine this into a single series. And our lower indices of summation are different. We prefer that those be the same. So what's interesting about this one is you can correct both of them at the same time. Notice if I decrease my index of summation by 2, I'm going to have to increase each of these n's by 2. That's going to make this one n plus 1, c sub n plus 2. But look what happens to my exponent. If I increase it by 2, I get x to the nth power. I'm also going to transfer this 4 inside the summation symbol. And I can see now that both my lower limit of summation and the power on x match. What that means is I can go ahead and equate corresponding coefficients. So we know n plus 2 times n plus 1 times c sub n plus 2, the coefficient of x to the nth power on the left, is equal to the coefficient of x to the nth power on the right. Notice that I'm setting an infinite number of coefficients equal to each other, corresponding them by their subscript n. So this is a very efficient process. Now, it's convenient to solve for the later constant, c sub n plus 2, in terms of the previous constant, c sub n. So we're going to get 4c sub n divided by n plus 2 times n plus 1. So again, this is what we call a recursive or a recurrence relation. Although it does give me some information, I really need this in terms of an nth term formula. That is, I need the coefficients in terms of the position n, not previous constants c sub n. It's also a good idea to pay attention to where your index begins. This is going to be true for all n greater than or equal to 0. So let's begin generating coefficients to look for an inductive pattern. I'm going to start with n equals 0. If n equals 0, on the left side we'll have c sub 2. This is going to be equal to 4c naught. Plugging 0 in for n, we'd have 2 times 1, or 4c naught over 2 times 1. I'm not going to reduce. It's tempting, but again, I want to see the pattern develop here. Let's increment our index by 1. We have n equals 1. Plugging that into our recursive formula, we can see that c sub 3 is equal to 4c sub 1 divided by 1 plus 2, which is 3, times 1 plus 1, which is 2. Okay, so the first constant, C2, is in terms of C naught. The second one, C3, is in terms of C1. So at this point, they're not in terms of the same constant. Let's increment our index by 1 to get n equals 2. So I'm plugging in n equals 2. This will give me C sub 4 equals 4C sub 2 divided by 4 times 3. Now, this time we know C sub 2, so I'm going to replace C sub 2 with its definition up here and glue it all together. And notice we can see a factorial beginning to form in the denominator. Let's go another unit. Again, we have to keep building this until we're confident of the pattern. Plugging in 3 for n, we have 4 times C sub 3 over 5 times 4. This time, we know C sub 3 here, so plugging that in, we have 4 times 4 times C sub 1 divided by 5 times 4 times 3 times 2. So we're beginning to see the development of an interesting pattern. Each of these two terms are in terms of C naught and C1. And I can see that happening for the next two subsequent terms. Let's go 2 more terms so we can be completely confident of the pattern. For n equal to 4, we'd have C sub 6 equals 4 C sub 4 divided by 6 times 5. Plugging in what we know about C sub 4, this will be 4 times 4 times 4 C naught divided by 6 times 5 times 4 times 3 times 2 times 1. Definitely a factorial there. For n equal to 5, we have C sub 7 equals 4 C sub 5 divided by 5 plus 2, which is 7, times 5 plus 1, which is 6. Okay, so let's plug in what we know about C sub 5. We're going to have 4 times 4 times 4 C sub 1 divided by 4 times 6 times 5 times 4 times 3 times 2, and of course 1. So again, this pattern is reappearing that these two successive constants are in terms of C naught and C1. Now think about it. The reason that we're getting two parameters here, C naught and C1, is because we started with a degree 2 differential equation. That always requires 2 initial conditions to solve for those 2 unknown parameters. But the big question is, how am I going to condense this so that I can recognize what my coefficients are for the original power series solution that we assumed for the solution? Well, if we notice here, the constants that involve C naught have even coefficients, right? And the constants that involve C1 have odd subscripts. I think I said coefficients meaning subscripts, okay? There we go. So even subscripts correspond with C naught, and odd subscripts correspond with C sub 1. Well, we can program that in abstractly. In the form of a series, when we want to access only even coefficients or subscripts, we can define that as 2 times a number, okay? Now, I'm going to go from n to k, so I'm changing my index from n to k here so that I can separate out even and odd numbers. So if I look at all of the even coefficients, or the coefficients with an even subscript, I should say, we can see a pattern forming. It's some multiple of C naught. So I'm going to call this first one k equals 1. The second one k equals 2. Here we're looking at the third term in our even subscript coefficients. Notice that the power of 4 matches our k value. So we can say this is going to be 4 to the kth power. Each of those has a C naught, and notice in the denominator we have an even factorial. 2 factorial here, 4 factorial here, and 6 factorial here. The factorial is double our k value. So we could write that as 2k in parentheses factorial. Okay? Now we can do something similar for our coefficients with odd subscripts. We're going to call that 2k plus 1. In fact, I think it'll be a great idea to color code this so you can see the pattern very well. If 2k is an even number, 2k plus 1 is always going to be an odd number. So I'm going to call this one k equals 1 for my odd series, k equals 2, and then down here k equals 3. We're looking for patterns here. So looking at our first term, the first term in the odd series, that is, I notice that the power of 4 matches the k value. Okay, looking at our second term in our odd series, the power of 4 matches the k value, and the same thing is true here. So we can write this as 4 to the k power. Each of those multiplies the constant C sub 1. And notice in the denominator we have 3 factorial, 5 factorial. This one should be a 7 factorial. Okay, so we're going to have whatever our odd number is in the denominator with a factorial. So putting this all together, we can say, therefore, the solution to the system y, solution to our differential equation, here's our model, okay? We're going to separate it into even and odd terms. So the first one is going to go from k equals 0 to infinity. Our coefficient, that's going to be our even subscripted coefficients. That's going to go with an even power of x. Then for our odd subscripts, we're going to go from k equals 0 to infinity of c sub 2k plus 1 times x to the 2k plus 1. Okay, in this way, I have covered every power of x. This would be x to the 0th power, x to the 1st, x squared, x cubed, so on and so forth. Okay, so by switching those subscripts from n to k, we're spicing it up a little bit. Okay, let's fill in the details of our determined coefficients. So we have k equals 0 to infinity. I'm filling in the details for what we found out about the pattern of our even coefficient c sub 2k. It's 4 to the kth power times c naught divided by 2k factorial times our even power of x. Then we have the sum from k equals 0 to infinity. Filling in the information about c sub 2k plus 1, we found that to be 4 to the k times c sub 1 divided by 2k plus 1 factorial. And this will be multiplied by the odd powers of x. Now we're developing our power series solution here, but our goal eventually is to equate this to an elementary function from the list on page 1 of our notes. So I'm going to manipulate this just a little bit. First of all, I'm going to factor out the coefficient C0, and I'm going to rewrite 4 to the k as 2 squared. 4 is 2 squared, and then I'm going to raise the whole thing to the 2k power. And you can probably see the reason I'm doing that is because I see that repeating 2k in the rest of my factors. I'm going to do the same thing over here. I'm going to rewrite that 4 to the k as 2 to the 2k, C sub 1. Now this one is not quite a match, right? We have 2k on the exponent on the 2 and 2k plus 1 elsewhere. And let's also factor out our C sub 1 at this point. So I'm going to move that guy over here. Now let's make those 2k plus 1s match in our second series. So I prefer it to say 2 to the 2k plus 1. Okay, so that it's going to match the exponent here and the factorial in the denominator. But remember, I can't make that change arbitrarily without canceling it out somewhere else. So when I add 1 to the exponent, ultimately I'm multiplying by 2 to the first power. So I'm introducing an extra factor of 2 by adding 1 to that exponent. Well, if I have multiplied by 2, I need to divide by 2 to cancel out that change. And I'm going to take care of that over here with the coefficient. Okay, so it's a simple fix. Creative, but simple. So finally, we can write a very clean expression for our power series solution. This is going to be C0 times the sum from k equals 0 to infinity of 2x to the 2k, both of those have the same exponent, divided by 2k factorial, plus constant C1 over 2, times the sum from k equals 0 to infinity. Now 2 and x have the same exponent, so I can join those as a single base under a common exponent. And we're looking good. So this is the power series representation of the solution to our second order differential equation. Now my goal is to match this up with an elementary function. I do want to point out to you that right here in the base we have a 2x, so keep that in mind as we go back and look at our power series representation of elementary functions. This is page 1 of your notes. Recall that we examined 2 power series that split up even and odd powers of x. That was hyperbolic cosine and hyperbolic sine. If you look at the summation notation of those 2 series, it's essentially what we have. We have a k, these have an n, but that's no big deal. The difference between these 2 series is that we have a 2x raised to the 2k and a 2x raised to the 2k plus 1. So I can see that I'm manipulating the argument there. So we are dealing with hyperbolic cosine of 2x and hyperbolic sine of 2x. Okay, so let's replace our power series with these elementary functions. So we can rewrite our solution as an elementary function, C0. Now remember, the even powers went with hyperbolic cosine of 2x plus C sub 1 over 2 times hyperbolic sine of 2x. That is pretty amazing. Okay. Now let me ask you a question. If I had given you this differential equation, y double prime equals 4y, and I said solve it, you probably would not choose to subject yourself to this sort of mathematics. You probably would have said, awesome, those are constant coefficients. Let's use the characteristic equation. And if you did that, you would very quickly come up with the solution. It would be an exponential function. Okay, and remember, hyperbolic cosine and hyperbolic sine are equivalent to exponential functions. So why are we doing this? Again, So a couple of reasons. Number one, so we can see how power series represent elementary functions. You're going to get a better idea of how your calculator works and other mathematical technologies, but also you're learning a power series solution method which applies to more complicated differential equations. We're just beginners here, so we have to learn how to apply this method to the easier problems first. This is a pretty involved process, so let's try one more example. This should be example 4, so that we can learn the ins and outs of this process. So we have a second order linear homogeneous differential equation with constant coefficients, but we have initial conditions. So we're going to learn how to use initial conditions in the context of this power series solution. So let's make an assumption about the solution. Let y equal the sum from n equals 0 to infinity of c sub n times x to the nth power. Then y prime is going to be the sum from n equals 1 to infinity of n c sub n x to the n minus first. One more derivative, y double prime, will be the sum from n equals 2 to infinity of n times n minus 1 c sub n x to the n minus 2. Just applying the power rule there. Now we're going to sub this into our second order differential equation. Starting with our y double prime term, we write the sum from n equals 2 to infinity of n times n minus 1 c sub n x to the n minus 2. We're going to add this to the y prime term, which is the sum from n equals 1 to infinity of n c sub n x to the n minus 1. And we're going to subtract 2 times y, which is the sum from 0 to infinity, c sub n x to the n equals 0. Now our goal, as always, is to make our subscripts and powers on x match. So I'm going to decrease the index of summation by 2 and in the summation notation, which means I have to increase each of the n's by 2 in my formula. So this becomes c sub n plus 2. Adding 2 here gives me x to the nth power. We can do the same thing here. Decrease the lower limit of summation by 1. Increase my index by 1. That's going to give me x to the nth power here. I'm going to move the 2 inside the summation, but keep everything else the same for our last series. Okay, so that knocked out a lot of problems. Now x to the nth power is common throughout all of our series, and all series begin counting at n equals 0. So we can condense to a single series, n equals 0 to infinity. And while I'm at it, I'm going to factor out the x to the nth power. So we have n plus 2 times n plus 1 c sub n plus 2 plus n plus 1 times c sub n plus 1 minus 2c sub n, all of that times x to the nth power equals 0. And I'm recognizing we have an infinite degree polynomial function on the right side with all 0 coefficients. That means we can set all of our coefficients equal term by term using our formulas. So picking up our coefficient on the left, notice we have 3 constants here, c sub n plus 2, c sub n plus 1, and c sub n. So the practice is solve for your latest constant, c sub n plus 2, in terms of the earlier constants. So I'm going to add 2c sub n from both sides. I'm going to subtract n plus 1, c sub n plus 1 from both sides, and divide by the coefficient n plus 2 times n plus 1. Now I did find this one easier to work when I split that fraction into 2 separate constants. So I'm going to call it 2c sub n divided by n plus 2 times n plus 1 minus n plus 1 c sub n plus 1 divided by, same things, n plus 2 times n plus 1. And then you can see obviously your n plus 1s are going to cancel. So at this point, we have an infinite number of constants that we're attempting to determine, but don't forget, we had some initial conditions as part of our original problem. At this point, I'm going to go ahead and apply the initial conditions because that's going to give us some of our constants. So our first initial condition is y of 0 equals 1, okay? If you'll recall, we made the assumption that our solution y has the form, the sum from n equals 0 to infinity of c sub n times x to the nth power. If I expand that, that means c naught x to the 0th power plus c1 x to the first power plus c2 x squared, so on and so forth. Okay, now applying our initial condition, if we set y equal to 1 and we plug 0 in for all the subsequent x's, well, all of our terms from the second or the c sub 2 term on down are going to 0 out. So we discover at this point that c naught is equal to 1. So our first initial condition gives us information about our first constant. Our second initial condition was y prime of 0 was equal to negative 2. Okay, now remember we said y prime was the sum from n equals 1 to infinity of n c sub n x to the nth power. Okay, if I expand that a little bit, whoops, forgot my minus 1 there. If I expand that a little bit, we're going to have y prime equals, for n equals 1, we're going to have c sub 1 x to the 0th power. For n equals 2, we'll have 2 c sub 2 x to the first. For n equals 3, we'll have 3 c sub 3 x cubed, x squared, plus, and then that continues forever, right? Now, if we go ahead and apply our initial condition, we can set our derivative equal to negative 2, and we're plugging 0 in for x. So you can see every term is going to be annihilated by that 0 except for c sub 1. So now we know c sub 1 is equal to negative 2. So we know the first two constants, and that indicates that we're going to get a particular solution. So let's take the values of these two constants and go back to our recursive relation for our constants. Remember, this is going to be true for all n greater than or equal to 0, corresponding to our lower limit of summation. So let's start and generate some constants. For n equal to 0, we have c sub 2 equals 2c naught over 2 times 1 minus, we're plugging in n equal to 0, minus 2c1 minus c1 over 2. Plugging in c naught equal to 1 and c sub 1 equal to negative 2, we can evaluate this constant to be 4 over 2. And I'm not going to reduce it again because I'm looking for a pattern. Let's generate the next one. Increment n to be 1. Plugging in n equals 1 in our recurrence relation, we have c sub 3 equals 2c sub 1 over 3 times 2 minus, plugging in n equals 1, we have c sub 2 divided by 3. I'm going to get a common denominator here and plug in what we know. Okay, remember c sub 1 is equal to negative 2, and we just found c sub 2, if we reduce, is equal to 2. Combining our terms here, we would get negative 8 over 3 times 2. Okay, let's go one more term. N equals 2. Let's plug that into our recurrence relation. We'd have c sub 4 equals 2c sub 2 divided by 4 times 3 minus, plugging in n equals 2, we have c sub 3 divided by 4. Okay, I'm going to get a common denominator here. So if I plug in c sub 2 equals 2 and I plug this in for c sub 3, I'm going to end up with 8 over 4 times 3, okay? However, I'm looking for a pattern. So I notice a factorial beginning to develop in the denominator. So I'm going to multiply the top and the bottom by 2. So I have 16 over 4 times 3 times 2, okay? Now I can say, therefore, the nth coefficient is going to be, well, first of all, notice it's alternating. Here it's positive, here it's negative, and here it's positive. I also recognize that it's a power of 2. So we're going to have negative 2 to the nth power divided by n factorial. Okay, so notice 4 here is 2 squared, and I have a 2 factorial in the bottom. 8 is 2 cubed, and I have a 3 factorial in the bottom. 4 is 2 to the 4th power, and I have a 4 factorial in the bottom. We are now ready to express the power series solution to this differential equation. So we have found the coefficients. We're going to go back to the assumption of our solution and put it all together. We can say, therefore, y equals the sum from n equals 0 to infinity. Plugging in what we know about c sub n, we have negative 2 to the nth power over n factorial times x to the nth power. Simplifying, we obtain the sum from n equals 0 to infinity of negative 2x to the nth power over n factorial. This is the power series representation of the solution. Going back to page 1 of our notes, we have something that's very similar to this, but instead of an x in this position, we have a negative 2x, which is going to change the argument here. So our solution is e to the negative 2x. Therefore, back to our problem here, in a roundabout way, our particular solution is e to the negative 2x. So in a roundabout way, we got to the particular solution. I hope that this lesson increases your skills as far as manipulating power series. I hope it also helps you to understand that every elementary function can be expressed as a polynomial of infinite degree. Okay, that's pretty profound. In the same way that irrational numbers are the sum of an infinite number of rational numbers, we can say every elementary function is equivalent to some sort of infinite degree polynomial. Also, I hope that you learn this power series method and you get an idea of maybe the mechanics behind certain computer algebra systems and calculators. They're dependent on power series more than our simplified concept of elementary functions. So most of the differential equations in section 3.1 we can solve with methods we've learned previously, but now you understand the potential of power series to solve more complicated differential equations, specifically those with non-constant coefficients. Higher order non-constant coefficient differential equations can be solved with the power series method.